Hello everyone, this is Caller from 19. Today's day is 27, 26 in my challenge day. And what I'm going to do is about softmax classifier and softmax regression. And then going to uh, learn some introduction to programming frameworks like TensorFlow. And let's start.
So far, the classification examples we've talked about have used binary classification, where you had two possible labels, 0 or 1. Is it a cat or is it not a cat? What if you have multiple possible classes? There's a generalization of logistic regression called softmax regression that lets you make predictions where you're trying to recognize one of C or one of multiple classes rather than just recognize two classes. Let's take a look. Let's say that instead of just recognizing cats, you want to recognize cats, dogs, and baby chicks. So I'm going to call cats class 1, dogs class 2, baby chicks class 3, and if none of the above, then there's an other or a none of the above class, which I'm going to call class 0. So here's an example of the images and the classes they belong to. That's a picture of a baby chick, so the class is 3, cat is class 1, a dog is class 2. I guess that's a koala, so that's a none of the above, so that's class 0, class 3, and so on. So the notation we're going to use is, I'm going to use capital C to denote the number of classes you're trying to categorize your inputs into. do. And in this case, you have 4 possible classes, including the other or the none of the above class. So when you have 4 classes, the numbers indexing your classes would be 0 through C minus 1, through capital C minus 1. So in other words, it would be 0, 1, 2, or 3. In this case, we're going to build a neural network where the output layer has 4, or in this case, the variable capital alphabet C output units. So N, the number of units in the output layer, which is layer L, is going to be equal to 4, or more generally, is going to be equal to C. And what we want is for the number of units in the output layer to tell us what is the probability of each of these 4 classes. So the first node here is supposed to output, or we want it to output, the probability that is the other class, given the input x. This will output probability that is a cat, given x. This will output probability that is a dog, given x. That will output the probability. I'm just going to abbreviate baby chick to be BC. So probably have a baby chick abbreviated BC, given the input x. So here, the output labels y hat is going to be a 4 by 1 dimensional vector because it now has to output 4 numbers, giving you these 4 probabilities. And because probabilities should sum to 1, the 4 numbers in the output y hat, they should sum to 1. The standard model for getting a neural network to do this uses what's called a softmax layer in the output layer in order to generate these outputs. Let me write down the map and then we can come back and get some intuition about what the softmax layer is doing. So in the final layer of the neural network, you are going to compute as usual the linear part of the layer. So Z capital L, that's the Z variable for the final layer. So remember, this is layer capital L. So as usual, you compute that as WL times the activation of the previous layer plus the biases for that final layer. Now, having computed Z, you now need to apply what's called the softmax activation function. So the activation function is a bit unusual for the softmax layer, but this is what it does. First, we're going to compute a temporary variable, which I'm going to call t, which is e to the zl. So this is applied element-wise. So zl here, in our example, zl is going to be 4 by 1. It's a 4-dimensional vector. So t itself, e to the zl, that's an element-wise exponentiation. T will also be a 4 by 1 dimensional vector. Then the output, al, is going to be basically the vector t, but normalized to sum to 1. So al is going to be e to the zl divided by sum from j equals 1 through 4, because we have 4 classes of t subscript I. So another way of saying this is that AL is also a 4x1 vector, and the ith element of this four-dimensional vector, let's write that AL subscript I, this is going to be equal to TI over sum of TI. Okay. In case this math isn't clear, we'll do an example in a minute that'll make this clearer. So in case this math isn't clear, let's go through a specific example that will make this clearer. Let's say that you've computed ZL, and ZL is a four-dimensional vector. Let's say it's 5, 2, -1, 3. What we're going to do is use this element-wise exponentiation to compute this vector t. So t is going to be e to the 5, e to the 2, e to the -1, e to the 3. And if you plug that into a calculator, these are the values you get. E to the 5 is 148.4, e squared is about 7.4, e to the -1 is 0.4, and e cubed is 20.1. And so the way we go from the vector t to the vector AL is to just normalize these entries to sum to 1. So if you sum up the elements of t, if you just add up those four numbers, you get 176.3. So finally, AL is just going to be this vector t as a vector divided by 176.3. So for example, this first node here, this will output e to the 5 divided by 176.3, and that turns out to be a 0.842. So saying that for this image, if this is the value of z you get, the chance of it being class 0 is 84.2%. And then the next node outputs e squared over 176.3. That turns out to be 0.042. So it's 4.2% chance. The next one is e to the -1 over that, which is 0.002. And the final one is e cubed over that, which is 0.114. So about an 11.4% chance that this is class number 3, which I guess is the baby chain class, right? So there's a chance of it being class 0, class 1, class 2, class 3. So the output of the neural network, AL, this is also y hat. This is a 4x1 vector where the elements of this 4x1 vector are going to be these four numbers that we just computed. So this algorithm takes the vector ZL and maps it to four probabilities that sum to 1. And if we summarize what we just did to map from ZL to AL, this whole computation, computing the exponentiation to get this temporary variable t, and then normalizing, we can summarize this into a softmax activation function and say AL equals the activation function g applied to the vector ZL. The unusual thing about this particular activation function is that this activation function L, this whole computation, computing the exponentiation to get this temporary variable t, and then normalizing, we can summarize this into a softmax activation function and say AL equals the activation function g applied to the vector ZL. The unusual thing about this particular activation function is that this activation function g, it takes as input a 4x1 vector and it outputs a 4x1 vector. So previously, our activation functions used to take in a single real value input. So for example, example, the sigmoid and the value activation functions input a real number and output a real number. The unusual thing about the softmax activation function is because it needs to normalize across the different possible outputs, it needs to take in a vector of inputs and then outputs a vector. So what are the things that a softmax classifier can represent? I'm going to show you some examples where you have inputs x1, x2, and these feed directly to a softmax layer that has 3 or 4 or more output nodes that then outputs y-hat. So I'm going to show you a neural network with no hidden layer, and all it does is compute z1 equals w1 times the input x plus b, and then the output a1 or y-hat is just the softmax activation function applied to z1. So in this neural network with no hidden layer, it should give you a sense of the types of things a softmax function can represent. So here's one example with just raw inputs x1 and x2, a softmax layer with c equals 3 output classes can represent this type of decision boundary. Notice it's kind of a several linear decision boundaries, but this allows it to separate out the data into 3 classes. And in this diagram, what we did was we actually took the training set that's kind of shown in this figure and trained the softmax classifier with 3 output labels on the data, and then the color on this plot shows thresholding the outputs of the softmax classifier and coloring in the input based on which one of the 3 outputs had the highest probability. So you can maybe kind of see that this is like a generalization of logistic regression with sort of linear decision boundaries, but with more than 2 classes, with instead of the classes being just 0, 1, the classes can be 0, 1, or 2. Here's another example of the decision boundary that a softmax classifier can represent when trained on a dataset with 3 classes. And here's another one, right? So this is but one intuition is that the decision boundary between any 2 classes will be linear. That's why you see, for example, the decision boundary between the yellow and the red classes, that's sort of a linear boundary. Between the purple and red is not a linear decision boundary. Between the purple and yellow is another linear decision boundary. But, you know, it's able to use these different linear functions in order to separate the space into 3 classes. Let's look at some examples with more classes. So this example with c equals 4, so that the green class and softmax can continue to represent these types of linear decision boundaries between multiple classes. So here's one more example with c equals 5 classes, and here's one last example with c equals 6. So this shows the type of things a softmax classifier can do when there is no hidden layer. Of course, you have a much deeper neural network with x and then, you know, some hidden units and then more hidden units and so on. Then you could learn even more complex nonlinear decision boundaries to separate out multiple different classes. So I hope this gives you a sense of what a softmax layer, what a softmax activation function in a neural network can do. In the next video, let's take a look at how you can train a neural network that uses a softmax layer. In the last video, you learned about the softmax layer and the softmax activation function. In this video, you deepen your understanding of softmax classification and also learn how to train a model that uses a softmax layer. Recall our earlier example where the output layer computes ZL as follows. So if you have 4 classes, C equals 4, then Z also can be 4 by one-dimensional vector. And we said we compute T, which is this temporary variable that performs element-wise exponentiation. And then finally, if the activation function for your output layer, G of L, is the softmax activation function, then the output will be this. It's basically taking that temporary variable T and normalizing it to sum to 1. So this then becomes A of L. So you notice that in the Z vector, the biggest element was 5, and the biggest probability ends up being this first probability. The name softmax comes from contrasting it to what's called a hardmax, which would have taken the vector Z and mapped it to this vector. So hardmax function will look at the elements of Z and just put a 1 in the position of the biggest element of Z, and then zeros everywhere else. And so this is a very hard max where the biggest element gets an output of 1 and everything else gets an output of of 0. Whereas in contrast, the softmax is a more gentle mapping from Z to these probabilities. So I'm not sure if this is a great name, but at least that was the intuition behind why we call it a softmax. Is in contrast to the hard max. And one thing I didn't really show, but had alluded to, is that softmax regression, or the softmax activation function, generalizes the logistic activation function to C classes rather than just 2 classes. And it turns out that if C is equal to 2, then softmax with C equals to 2 essentially reduces to logistic regression. And I'm not going to prove this in this video, but the rough outline for the proof is that if C equals to 2 and if you apply softmax, then the output layer, AL, will output two numbers if C equals 2. So maybe it outputs 0.842 and 0.158, right? And these two numbers always have to sum to 1. And because these two numbers always have to sum to 1, they're actually redundant. And maybe you don't need to bother to compute two of them. Maybe you just need to compute one of them. And it turns out that the way you end up computing that number reduces to the way that logistic regression is computing its single output. So that wasn't much of a proof, but the takeaway from this is that softmax regression is a generalization of logistic regression to more than 2 classes. Now, let's look at how you would actually train a neural network with a softmax output layer. So in particular, let's define the loss function you use to train your neural network. Let's take an example. Let's say you have an example in your training set where the output is, where the target output, the ground truth label is 0100. So the example from the previous video, this means that this is an image of a cat because it falls into class 1. And now let's say that your neural network is currently outputting y hat equals, so y hat would be a vector probability, it's got to sum to 1, 0.1, 0.4. So you can check that sums to 1, and this is going to be a L. So the neural network is not doing very well in this example because this is actually a cat and assigned only a 20% chance that this is a cat. So it didn't do very well in this example. So what's the loss function you would want to use to train this neural network? In softmax classification, the loss we typically use is negative sum of j equals 1 through 4, and it's really sum from 1 to c in the general case. I'll just use 4 here, of y log, or yj log y hat of j. So let's look at our single example above to better understand what happens. Notice that in this example, y1
2,
y1 equals y3 equals y4 equals 0, because those are zeros and only y2 is equal to 1. So if you look at this summation, all the terms with 0 values of yj will equal to 0, and the only term you're left with is negative y2 log y hat 2, because when you sum over the indices of j, all the terms will end up 0 except when j is equal to 2. And because y2 is equal to 1, this is just negative log y hat 2. So what this means is that if your learning algorithm is trying to make this small, because you use gradient descent to try to reduce the loss on your training set, then the only way to make this small is to make this small, and the only way to do that is to make y hat 2 as big as possible. And these are probabilities, so it can never be bigger than 1. But this kind of makes sense, because if x, for this example, is a picture of a cat, then you want that output probability to be as big as possible. So more generally, what this loss function does is it looks at whatever is the ground truth class in your training set, and it tries to make the corresponding probability of that class as high as possible. If you're familiar with maximum likelihood estimation in statistics, this turns out to be a form of maximum likelihood estimation. But if you don't know what that means, don't worry about it. The intuition we just talked about will suffice. Now, this is the loss on a single training example. How about the cost, J, on the entire training set? So the cost of setting the parameters, and so on, of all the weights and biases, you define that as pretty much what you guess, sum over your entire training set of the loss, your learning algorithm's predictions, summed over your training examples. And so what you do is use gradient descent in order to try to minimize this cost function. Finally, one more implementational detail. Notice that because c is equal to 4, y is a 4 by 1 vector, and y hat is also a 4 by 1 vector. So if you're using a vectorized implementation, the matrix capital Y is going to be y1, y2 through ym stacked horizontally. And so, for example, if this example up here is your first training example, then the first column of this matrix Y will be 0, 1, 0, 0, and then your second example, maybe the second example is a dog, maybe the third example is a none of the above, and so on. And then this matrix capital Y will end up being a 4 by m dimensional matrix. And similarly, Y hat will be Y hat 1 stacked up horizontally going through Y hat m. So if this is actually Y hat 1, or the output on the first training example, then Y hat will be this 0.3, 0.2, 0.1, 0.4, and so on. And Y hat itself will also be a 4 by m dimensional matrix. Finally, let's take a look at how you'd implement gradient descent when you have a softmax output layer. So this output layer will compute ZL, which is C by 1 in our example, 4 by 1, and then you apply the softmax activation function to get AL, or Y hat, and then that in turn allows you to compute the loss. So we've talked about how to implement the forward propagation step of the neural network to get this output and to compute that loss. How about the back propagation step, or gradient descent? Turns out that the key step or the key equation you need to initialize backprop is this expression that the derivative with respect to z at the last layer. This turns out you can compute as y hat, the 4 by 1 vector, minus y, the 4 by 1 vector. So you notice that all of these are going to be 4 by 1 vectors when you have 4 classes, and c by 1 in the more general case. And so this, going by our usual definition of what is dz, this is a partial derivative of the cost function with respect to zl. If you're an expert in calculus, you can derive this yourself. Or if you're an expert in calculus, you can try to derive this yourself, but using this formula will also just work fine if you ever need to implement this from scratch. But with this, you can then compute DZL, and then sort of start off the backprop process to compute all the derivatives you need throughout your neural network. But it turns out that in this week's programming exercise, we'll start to use one of the deep learning programming frameworks. And for those programming frameworks, usually it turns out you just need to focus on getting the forward prop right. And so long as you specify the programming framework, the forward prop pass, the programming framework will figure out how to do backprop, how to do the backward pass for you. So this expression is worth keeping in mind for if you ever need to implement softmax regression or softmax classification from scratch, although you won't actually need this in this week's programming exercise because the programming framework you use will take care of this derivative computation for you. So that's it for softmax classification. With it, you can now implement learning algorithms to categorize your inputs into not just one of two classes, but one of C different classes. Next, I want to show you some of the deep learning programming frameworks, which can make you much more efficient in terms of implementing deep learning algorithms. Let's go on to the next video to discuss that. You've learned to implement deep learning algorithms more or less from scratch using Python and NumPy. And I'm glad you did that because I wanted you to understand what these deep learning algorithms are really doing. But you find that as you implement more complex models, such as convolutional neural nets or recurrent neural networks, or as you start to implement very large models, that is increasingly not practical, at least for most people, is not practical to implement everything yourself from scratch. Fortunately, there are now many good deep learning software frameworks that can help you implement these models. To make an analogy, I think that hopefully you understand how to do a matrix multiplication, and you should be able to implement, how to code to multiply two matrices yourself. But as you build very large applications, you probably not want to implement your own matrix multiplication function, but instead you want to call a numerical linear algebra library that could do it more efficiently for you. But it still helps that you understand how multiplying two matrices work. So I think deep learning has now matured to that point where it's actually more practical and you'll be more efficient doing some things with some of the deep learning frameworks. So let's take a look at the frameworks out there. Today, there are many deep learning frameworks that makes it easy for you to implement neural networks, and here are some of the leading ones. Each of these frameworks has a dedicated user and developer community, and I think each of these frameworks is a credible choice for some subsets of applications. There are a lot of people writing articles comparing these deep learning frameworks and how well these deep learning frameworks changes. And because these frameworks are often evolving and getting better month to month, I'll leave you to do a few internet searches yourself if you want to see the arguments on the pros and cons of some of these frameworks. But I think many of these frameworks are evolving and getting better very rapidly. So rather than too strongly endorsing any of these frameworks, I want to share with you the criteria I would recommend you use to choose frameworks. One important criteria is the ease of programming, and that means both developing the neural network and iterating on it, as well as deploying it for production, for actual use by thousands or millions or maybe hundreds of millions of users, depending on what you're trying to do. A second important criteria is running speeds, especially if you're training on large data sets. Some frameworks will let you run and train your neural network more efficiently than others. And then one criteria that people don't often talk about, but I think is important, is whether or not the framework is truly open. And for a framework to be truly open, it needs not only to be open source, but I think it needs good governance as well. Unfortunately, in the software industry, some companies have a history of open sourcing software, but maintaining single corporation control of the software. And then over some number of years, as people start to use their software, some companies have a history of gradually closing off what was open source, or perhaps moving functionality into their own proprietary cloud services. So one thing I pay a bit of attention to is how much you trust that a framework will remain open source, for a long time rather than just being under the control of a single company, which for whatever reason may choose to close it off in the future, even if the software is currently released under open source. But at least in the short term, depending on your preferences of language, whether you prefer Python or Java or C++ or something else, and depending on what application you're working on, whether it's computer vision or natural language processing or online advertising or something else, I think multiple of these frameworks could be a good choice. So that's it on programming frameworks. By providing a higher level of abstraction than just a numerical linear algebra library, any of these programming frameworks can make you more efficient as you develop machine learning applications. Hi, and welcome back. There are a few deep learning programming frameworks that can help you be much more efficient in how you develop and use deep learning algorithms. One of these frameworks is TensorFlow. What I hope to do in this video is step through with you the basic structure of a TensorFlow program so that you know how you could use TensorFlow to implement such programs, implement neural networks yourself. And then after this video, I'll leave you to dive into some more of the details and gain practice programming with TensorFlow in this week's programming exercise. This week's programming exercise does require a little extra time, so please do plan or budget for a little bit more time to complete it. As a motivating problem, let's say that you have some cost function j that you want to minimize. And for this example, I'm going to use this highly simple cost function j of w equals w squared minus 10w plus 25. So that's the cost function. You might notice that this function is actually w minus 5 squared. If you expand out this quadratic, you get the expression above. And so the value of w that minimizes this is w equals 5. But let's say we didn't know that, and you just have this function. Let's see how you can implement something in TensorFlow to minimize this. Because a very similar structure of program can be used to train neural networks, where you can have some complicated cost function j of wb depending on all the parameters of your neural network. And then similarly, you'll be able to use TensorFlow to automatically try to find values of w and b that minimize this cost function. But let's start with the simpler example on the left. So here I am in Python in my Jupyter notebook. In order to start up TensorFlow, you type import numpy or numpy as np, import TensorFlow as tf. So this is idiomatic. This is what pretty much everyone types exactly to import TensorFlow as tf. Next thing you want to do is define the parameter w. In TensorFlow, you're going to use tf.variable to signify that this is a variable, initialize it to 0, and the type of the variable is a floating point number. So dtype equals tf.float32. This is a TensorFlow floating point number. Next, let's define the optimization algorithm we're going to use. In this case, the Adam optimization algorithm. So optimizer equals tf.keras.optimizers.adam. And let's set the learning rate to 0.1. Now we can define the cost function. Remember, the cost function was w squared minus 10w plus 25. So let me write that down. The cost is w squared minus 10w plus 25. The great thing about TensorFlow is you only have to implement forward prop. That is, you only have to write the code to compute the value of the cost function, and TensorFlow can figure out how to do the backprop or do the gradient computation. One way to do this is to use gradient tape. Let me show you the syntax. With tf.gradient tape as tape, compute the cost as follows. The intuition behind the name gradient tape is by an analogy to the old school cassette tapes, where gradient tape will record the sequence of operations as you're computing the cost function in the forward prop step. And then when you play the tape backwards, record the sequence of operations as you're computing the cost function in the forward prop step. And then when you play the tape backwards, in backwards order, it can revisit the order of operations in reverse order. And along the way, compute backprop and the gradients. Now, let's define a training step function to loop over. I'm going to define a single training step as this function. In order to carry out one iteration of training, you have to define what are the trainable variables. So trainable variables is just a list with only W. And we're then going to compute the gradients with this, with the tape, cost trainable variables. Having done this, you can now use the optimizer to apply the gradients, and the gradients are grads and trainable variables. And the syntax we're going to use is we're actually going to use the zip function, it's a built-in Python function, to take the list of gradients, take the list of trainable variables, and pair them up so that the gradients and the zip function just takes these two lists and pairs up the corresponding elements. I'm going to type print W here just to print the initial value of W. We've not actually run train step yet. So, all right, hopefully I have no syntax errors. So W is initially the value of 0, which is what we have initialized it to. And now let's run one step of our little learning algorithm and print the new value of W. And now it's increased a little bit from 0 to about 0.1. Now let's run 1,000 iterations of our train step. So for I in range, 1,000 train step, print W, and let's see what happens. Run pretty quickly. And now W is nearly 5, which we knew was the minimum of this cost function. So isn't that cool? We just specified the cost function, didn't have to take the derivatives, and TensorFlow figured out how to minimize this for us. I hope this gives you a sense of the broad structure of a TensorFlow program. And as you do this week's programming exercise and play more with TensorFlow code yourself, some of these functions that I just used here will become more familiar. Just a couple things to notice. W is the parameter you want to optimize. So that's why we declared W as a variable. And all we had to do was use a gradient tape to record the order of the sequence of operations needed to compute the cost function. And that was void prop. And TensorFlow could figure out automatically how to take derivatives with respect to the cost function. And that's why in TensorFlow, you basically have to only implement the forward prop step, and it will figure out how to do the gradient computation. Now, there's one more feature of TensorFlow that I want to show you. In the example we went through so far, the cost function is a fixed function of the parameter or the variable W. But what if the function you want to minimize is a function of not just the parameters, of not just W, but also a function of your training set? So let's say you have some training data X and X or Y, and you're training a neural network where the cost function depends on your data, X or X and Y, as well as the parameters W. How do you get that training data into a TensorFlow program? Let's go through another version of how to implement all this. I'm still going to define W as the variable. Also going to use the Adam optimizer, but now I'm going to define X as a list of numbers, as an array, and I'm going to plug in 1, -10, and 25, and this will be another float 32. So these three numbers, 1, -10, and 25, will play the role of the coefficients of the cost function. So you can think of X as being like data that controls the coefficients of this quadratic cost function. So let me now define the cost function, which we're going to minimize as the 10 and 25, the parameters W. How W, but also a function of your training set. So let's say you have some training data X and X or Y, and you're training a neural network where the cost function depends on your data, X or X and Y, as well as the parameters W. How do you get that training data into a TensorFlow program? Let's go through another version of how to implement all this. I'm still going to define W as the variable. Also going to use the Adam optimizer, but now I'm going to define X as a list of numbers, as an array, And I'm going to plug in 1, -10, and 25. And this will be another float 32. So these three numbers, 1, -10, and 25, will play the role of the coefficients of the cost function. So you can think of x as being like data that controls the coefficients of this quadratic cost function. So let me now define the cost function, which we're going to minimize as same as before, except that now I'm going to write x of 0 times that plus x of 1 times that, no, so this plus x2. So this is the same cost function as the one above, except that the coefficients are now controlled by this little piece of data, x, that we have. So now this cost function computes exactly the same cost function as you had above, except that this little piece of data in the array x controls the coefficients of the quadratic cost function. Now, let me write print w. This should do nothing because w is still 0. It's just the initial value. But if you then use the optimizer to take one step of the optimization algorithm, then let's print w again. Let's see if that works. Great. Now this has taken one step of Adam optimization, and so w is again roughly 0.1. So the syntax optimizer.minimize cost function and then list of variables w, that is a simpler alternative piece of syntax, or does the same thing as these lines up above with the gradient tape and apply gradients. Now that we have a single training step implemented, let's put the whole thing in a loop. Def training x w optimizer, define the cost function within the scope of this function, and then for I in range 1000, let's run 1,000 iterations, and then we will return w. So let's see what that does. There you go. And now w is nearly at the minimum, set to roughly the value of 5. So hopefully this gives you a sense of what TensorFlow can do. And the thing that makes it so powerful is all you need to do is specify how to compute the cost function. And then it takes derivatives and it can apply an optimizer with pretty much just 1 or 2 lines of code. So here's the code again. And in case some of these functions or variables still seem a little bit mysterious to you, they will become more familiar after you've practiced with it a couple times by working through the programming exercise. So what is this code really doing? Let's focus on this equation. The heart of a TensorFlow program is something to compute the cost, and then TensorFlow automatically figures out the derivatives and how to minimize the cost. So what this line of code is doing is allowing TensorFlow to construct a computation graph. And what a computation graph does is the following. It takes x0 and it takes w, and w gets squared, so that's w squared, and then x0 and w squared get multiplied together to give x0 times w squared, and so on through multiple steps until eventually this gets built up to compute the cost function. I guess the last step would have been adding in that last coefficient, x2. The nice thing about TensorFlow is that by implementing basically forward prop through this computation graph, TensorFlow will automatically figure out all the necessary backward calculations. And it'll automatically be able to figure out all the necessary backward steps needed to implement backprop. Isn't that nice? And that's why you don't need to explicitly implement backprop. TensorFlow figures it out for you. And this is one of the things that makes the programming frameworks help you become really efficient. And there are also a lot of things you can change with just one line of code. For example, if you don't want to use the Atom optimizer and you want to use a different one, then just change this one line of code. And you can quickly swap it out for a different optimization algorithm. All of the popular modern deep learning programming frameworks support things like these, and it makes it much easier to develop even pretty complex neural networks. So I hope that gave you a sense of the typical structure of a TensorFlow program. To recap material from this week, you saw how to systematically organize the hyperparameter search process. You also saw batch normalization and how you can use that to speed up your neural network training. And we also chatted about deep learning programming frameworks, and you learned about TensorFlow. I hope that you go on and try out and enjoy this week's programming exercise, which will help you to gain even greater familiarity with these ideas.
Okay, I just finished the entire course too, and what I had to do is a programming exercise. So the things that I learned today is about multi-class classification and about deep learning frameworks in the modern deep learning era. Now, about the classification problems, we've already always done with the binary classification, like classify whether it is a cat or not, or whether it's dog or not. We have only always have two classes in the problem. But in most cases, we may have more classes in the problem. Like it is described in this image, the label 3 is corresponding to baby chick, and 2 for dog, and 1 for cat, and none of them is 0. So we have 4 possible cases in the problem. So in this problem, we need to change the output layer a bit. So we expand the number of units in the output layer. So in these specific cases, we have 4 units in the output layer. So the dimension of the activation parameter GL, the layer at G at the layer L becomes 4 rows and 1 column. And for softmax layer, we also use different activation function. So we first the element-wise explanation first, element-wise. So with the given GL, we exponentiate the GL to a temporary vector. And we do a normalization using the T by summing up the T's components and by dividing up the exponentiated G. So in the logistic regression example, it made a single number of output, uh, but in the softmax activation function, because the dimension of both output and input is equal to the number of classes, is corresponding to number of classes. So we have its shape, its result is kind of similar to logistic regression, but it's more generalized version of logistic regression. As you can see, if it was a logistic regression, we have two classes. So all we need to have, what we need, the only thing we have is just one line of linear regression. But in the softmax, we have a several line of partitions in the results. The next topic is about training a softmax classifier. Um, Following these above examples, we can get the activation values, which is the activation vector, like this. And the softmax name is originate from the contrast of the hardmax. If we use a hardmax, just the maximum value 5 in here. So we just don't care about any other values except for this maximum in hardmax. So it can be the 1000 because we don't need to care about other smaller values than the maximum. But in the softmax, we take a soft approach to take a max by using the by using the normalization. So we keep the probability of the each of the values, but still the maximum is maximum in the softmax is vector. So in the network computation, it's always important that how to get a loss function and the cost function. So for the just a single loss, we can represent the loss as like this. To understand these formulas intuitively, let's put in the ground truth label into here. The second unit is corresponding to a second label corresponds to cat, and the other is just zero. So if we just expand this equation, we can see that all the terms can be zero except for the y underscore 2. So we can rewrite this equation like this just for the specific case here. And because y2 is equal to 1, what we have only is the minus log y hat 2. Um, by definition of loss function, we want to make this loss function small because the log function looks like this, and we invert it by multiplying minus. It will graph plotted like this downside. So to make this loss function small, the only way to do that is to make y hat is big. So y hat is underlined to x-axis. So if we make the y hat is bigger, so we can just get the loss function smaller with the linear gradient descent. So about the entire cost function, it's just these equations for just a single loss. So to sum up the whole loss in the entire cost function for the entire cost function, we can just use this. We can follow this function and the average it. And the key difference between the logistic regression and softmax regression in the gradient descent is also is about just loss layer because we have different activation function like this. It was a sigmoid function in the logistic regression. So it's kind of painful to implement all of the backpropagation ourselves. Every time, whenever we change the cost functions, we need to compute the backpropagation again. But if we use the deep learning frameworks in the machine learning field, it can be more easier. So first, tips for choosing the good deep learning frameworks is it need to be easy to programming with those libraries and those frameworks. And it should be it should has a good running speed, and it should be truly open because not all of the open source is has a good governance. So we need to care about um, the open source, whether it has a good governance or not. So in this course, we use a TensorFlow. So motivation for TensorFlow, let's take an example. Like we have these cost functions. So to manually implement these um, uh, for our neural network with this cost function, we need to compute these back propagation of this cost function. Like you might remember that in the first course, 4 week 2, week 1. Okay. Week 2. As you can see, following the computation graph in the forward propagation, to get a back propagation step, we following the computation graph in the reverse order. So in our manual implementation, we need to do this manually. So the free derivative of dj with the w parameters, it will be 2w minus 10, and the minimum gradient descent is equal to w is equal to 5. So our answer is 5. We need to find 5 by using our model. But let's see how we can simplify this in TensorFlow. In TensorFlow, we only need to care about the forward propagation and the cost function, which is the cost function, because if we record the forward propagation steps with the tape, it records a computation graph inside a cache. And when we do a backpropagation, it uses the tape in a reverse order. So it deduces the steps, all of each backpropagation steps automatically for us. So what we need to do just set up the proper for the propagation steps. Also, you can see we can use optimizer we learned in the previous section, like Adam, Armis, prop, and momentum. Really easy to change the several optimizer, just setting up another values and another variables. Really easy. And as you can see, we can just compute the backpropagation using a gradient method in the tape. Really easy. So this is the end of for course 2, and thanks for watching.